السلام عليكم ورحمة الله وبركاته. يسعد صباحكم يا شباب. اليوم إن شاء الله هنكمل بهذا الشابتر. وصلنا لهذا السلايد. المحاضرة الماضية حكينا عن cylinder sphere for a single layer. Now if we have multi-layered cylindrical sphere, okay, let me change the color. So multi-layer cylinder and the sphere. So here in this figure we'll see the thermal resistance network for heat transfer through three layered composite cylinder. So this is composite because we have more than one material, okay, and we have here cylinder subjected to convection in both sides. So here we have convection H due to convection, and here we have convection on the other side, okay, and here we have three layer of different material composite cylinder layers, okay. Now layer 1 or K1, the inner radius R1 and outer radius R2, the layer number 2 inner radius R2 and outer radius R3, and layer number 3 inner radius R3 and outer radius R4, okay. So if I need to calculate if I need to draw the resistance network, so I have to draw 5 resistance. This is resistance 1, here resistance 2, okay, 3, okay, 4, and this is resistance 5. In this arrangement, all of these resistance are on series, as you can see here in this resistance network, all of them on series. So here are convection 1 and this is our convection 2 at the outside of the cylinder, okay. This is our cylinder 1, this is conduction, okay. This is our due to convection, this one is due to conduction, this one due to conduction are cylinder 2, and here are cylinder 3. Once they are on series, then if I need R total, then I have to add them, okay. So the conduction resistance of the cylindrical layers equal to R1, R convection 1 plus R cylindrical 1. So R convection 1, which is equal to 1 over H1 multiplied by area 1, okay, where H1 is the convection and area 1, once we are talking about layers, then this is equal to 2 by R1 multiplied by, this is 1, okay, multiplied by L of the cylinder, okay. Now our cylinder from previous lecture equal to ln. So if let me take our cylinder 2, layer number 2, this one, okay, this one. So our cylinder 2 equal ln from the equation ln outer radius divided by inner radius. Outer radius for layer number 2 is R3, correct, divided by R2 divided by 2 by L, and since we are talking about layer 2, this is K2, okay. So this is for cylinder 2 and etc, okay. So convection resistance 1 over H1A1 R cylinder 1 ln R2 over R1 divided by 2 by LK1 and etc. Cylinder 3 outer radius, which is R4 divided by R3 divided by 2 by LK3, and here this is the R convection 2. Conduction resistance of a spherical layer. So same drawing, we can use same drawing, but for spherical layer, the same R total, we have convection, okay, but the only difference is with the R cylindrical, okay, this one. So R conduction for spherical, the equation R spherical. Okay, so if I need R spherical again for layer 2, this is equal to R outer, which is R3 minus R2 over 4 by R2 R3 multiplied by K. Okay, and everything else the same. R convection 1 remain the same, 1 over area 1 في H1, but the only difference is area. Okay, what is the perpendicular area with the cube for spherical case? I think I explained it before, so please go back and check. Okay. Now here, if we have multi-layer, we'll ask the same question. Okay, so sometimes we need to find out T2. This one, everything known, we could calculate Q from T infinity 1 and T infinity 2 divided by R total. And in the other part of the problem, he asked us to find T2. Okay, so T2 either we come from this side or we come from this side. Okay, so once heat transfer rate Q dot has been calculated from previous equation, T infinity 1 minus T infinity 2 over R total, the interface temperature T2 can be determined from any of the following two relations. So either we can come from this side or from this side. So Q equal T infinity 1. So this is which side? Side number 1. Okay. So in side number 1, those are the junction, and we have between them R convection 1 and R1. You can see them here. Okay, R convection 1 over H1 area 1 and R cylindrical 1. So in this case we have here cylinder. Okay, so it's not written here cylinder, but we'll assume it's cylinder. If it is spherical, we'll substitute R spherical here. Okay, so assume that we have here R cylinder. Okay, then this is ln R2 over R1 divided by 2 by LK1. Or we have another scenario. Okay, so we can come from the other side and we name it to this side, which is equal to T2 minus T infinity 2 divided by resistance between them, R2 plus R convection 2. Okay. Okay. Now, the last topic here in spherical and cylindrical is the critical radius of insulation. Okay, I ask you at the beginning of this chapter that, or I did not ask you, I demonstrate to you the objective of this chapter, and one of the objective was the insulation. If we are increasing the thickness of insulation, may increase heat transfer. And at that time, you asked me why it's increased. We add insulation to decrease heat transfer, to minimize heat loss. Okay, so this is the benefit of adding insulation to wall, for example, to minimize heat transfer from inside to inside, from outside to inside, or the opposite. Okay, so let's see why, if we add sometimes if we add insulation, the heat transfer increase. So why? Let us see. Now the answer of this question, whether it's increase or decrease, depend on the geometry that we are dealing with. Either we'll have wall, okay, or we have cylinder, okay, or we have sphere. Okay, so adding more insulation, so this is the first scenario for wall. So adding more insulation to a wall, always, what is the result of adding insulation to first geometry, which is wall? Always decreases heat transfer. دائما بقلل الضياع في الحرارة، دائما بمنع الحرارة إنها تطلع خارج. مثلا لو بندفي بيت وضفنا insulation، كل ما زدت الثيكنس لهذه الانسوليشن كل ما كان أحسن. اوكي، بس مش معناه أضلني أزيد، لأنه حتكون in terms of cost. Okay, so it is good to add insulation, so it will insulate inside from outside in terms of heat, but in terms of cost you will pay a lot. Okay, and as engineering we are do like compensation between solutions. Okay, we need to minimize the cost as well as we need to minimize the losses in terms of heat transfer. Okay, so if you add insulation, if you keep adding insulation دائما ايش بيكون عندنا الكيس؟ دائما decrease. Okay, decrease heat transfer, since heat transfer area is constant. So if I in a few moments I will show to you the equation. Okay, why we mention the surface area, why it is constant. Okay, so and adding insulation always increases the thermal resistance, okay, of a wall without increasing convection resistance. Okay, so here we mentioned too many parameters. Here the surface area, okay, and we mentioned thermal resistance of the wall, R wall, okay, and at the end we mentioned the convection resistance. This is 3, R convection, and this is always the case. Whenever you add more thickness, more insulation, or more material, you increase the thickness of insulation. What happens? The transfer area keep constant. This is first parameter. R wall always increased. Okay, دائما هذا R wall increased. Okay, and this R convection remain constant. Nothing happened to this one. Okay. Okay, let's see the other scenario, cylinder and sphere. Okay, so this is the other scenarios, other geometries. So we saw this one. Now let's see what happened. Both of them gathered in this statement. In a cylindrical pipe or a spherical shell, okay, the additional insulation, if you keep adding insulation, sometimes increases the conduction resistance of the insulation, or it's not sometimes, always. Okay, دائما هذا الاشي بصير. So if you keep adding, this is first parameter affected, R wall بتزيد. Okay, the resistance بتزيد زي نفس هذه. So R wall here increased في حالة الوول. Okay, but R wall في حالة السpherical والcylindrical أنا ممكن أسميها cylindrical عشان ما تخربطوا. Okay, increases of the insulation layer, but the other factor, but decreases the convection resistance. So here R convection in previous geometry wall, R convection remain constant, but here R convection decrease. Okay, why it decrease? Because of the increase of the outer surface area for convection. Okay, so the outer surface area out, this is the third parameter. Okay, and we can combine them in one parameter. So R out increase. Okay, but here area remain constant. So here area out remain constant. So this is the main difference. Why when we add insulation to wall, it's good, but here if you keep adding insulation, if you increase the thickness up to critical point, then this insulation will work in the opposite function. Okay. The heat transfer from pipe may, so as a result, for the cylindrical, for example, or spherical, but for cylindrical, the heat transfer from pipe may increase or decrease depending on which effect dominates. Okay, so which two effect? Those two effects. We have our insulation. Okay, because insulation, if this is our cylinder or sphere, okay, in blue color, okay, and we add insulation in the gray color, okay, this one. So this is our insulation, okay, here, this one, okay. So this is resistance of our insulation, and we have here outside our convection. So here we have two parameters. So let's first talk about wall. Okay, let's first talk about wall. So if we have wall made of certain material and then we add insulation, so we have here again insulation, and outside we have our convection. Okay, and here we have our wall. So what happened here? Our insulation, in this case, do you know what? Let me move to solving board. Maybe it will be clearer for you. Okay, so here we have wall, and I want to add insulation. So here is the insulation. So, and here is the resistance network. So this is our insulation, and we can call it our wall, which is equal to, what is the equation for arc conduction for wall geometry? L over K. Okay, and here our convection equal to 1 over HA. Okay, so if I want to write the equation, Q equal, okay, T1, I can call it, if this is T1 here at the interface, okay, minus T infinity divided by R insulation plus R convection. Now, here we have only one parameter, because this one, as I mentioned in the text, remain constant. Why it is remain constant? So here, this is the insulation. Sometimes we wish to add thicker insulation. So when we add thicker insulation, we have only one parameter change, which is the thickness, X. But in terms of area, this area here, the side area, this one, remain constant in both thickness. So this one remain constant area, and this one remain constant. So this parameter remain constant in the wall. Okay, so this one will not change. So it is not a parameter. The only one change is the R insulation. Which parameter inside the R insulation? The thickness, this parameter. So as long as we increase the thickness, what happened to R? R will increase. So if we increase R in the denominator, Q will decrease. Okay, and this is the function of insulation, of adding insulation. So if you add insulation, you will minimize heat loss, or you will resist the heat transfer through the wall. Okay, so دائما always once we increase L, Okay, once you add more insulation, what happen? R insulation increase as well as Q will decrease. This is always the rule for wall. But what happened for cylinder and sphere? So here is cylinder, for example, in a blue color, according to the slide. Okay, and we want to add insulation. So here is the insulation. Okay, and I will add another insulation. Okay, so I want to write the equation. So Q equal T1 according, this is T1. Okay, here between the cylinder and insulation. Okay, and here we have T infinity outside. So T1 minus T infinity over R insulation plus R convection. Okay, so R insulation, if we have here cylinder, then R insulation for the conduction case, which is equal ln R out over Rn, okay, divided by 2 by Lk, and this is R insulation, and R convection equal to 1 over H area out. Okay, now what happens if we start with this one, with this insulation? So this one, this is insulation 1, and in the other color we have insulation 2. This is insulation. We increase the insulation, the radius of the insulation. Okay, what happens if we add insulation 1? So if we add insulation 1, R out will increase. Okay, we add more insulation. So R insulation also will increase, correct? So this term increase. What is the expectation? Q must decrease, correct? But still, we cannot judge. We have another parameter. Which one? R convection. R convection here is not constant. What happens if we add first insulation layer? This area, R out, or area out, which is equal to by R out L, also increase this area. But be careful, this area in the denominator. What will happen if area increase or decrease? So this term will decrease. So we have one resistance increase and the other resistance decrease. So what will happen to Q? We have one parameter increase and we have another parameter decrease. This is why we said that here in this statement, heat transfer from pipe may increase or decrease depending which effect dominates. فإذا كان البارامتر مثلا R convection هو الدوميننت، هو العامل الأقوى، كان انخفاضه أكثر، okay. بالتالي Q will increase، okay. بس إذا كان R insulation هو الدوميننت، هو المؤثر الأقوى، what will happen to Q? Q will decrease، okay. So it may increase or decrease. So adding insulation for cylinder and sphere مش دائما بعطيني نقصان في الضياع، أحيانا بعطيني زيادة في الضياع based which parameter from these two are dominant. طيب كيف أنا بعرف؟ كيف ممكن مباشرة أحسبها بدون ما أتغلب؟ using critical radius of insulation. So take a look here. Here we have Q, and here we have cylinder. So the cylinder in black color, and the one in the blue color is insulation. Okay. Okay. Now, so here Q loss from inside to outside. So this is Q, and here we have R outer. Okay. So if we start from without, so this R1 without any insulation, we have certain amount of Q escape from the pipe. Okay, escape to outside. Now, if you start adding insulation, so Q keep increase, okay, until we reach certain point, Q start decreasing. So now you can tell me if this is without adding insulation, okay, if this is the plain case, the cylinder without any insulation, and once we starting adding insulation, Q increased, it means what? Which parameter is dominant in this scenario? From here, from this point up to this point. By the way, this point is called critical point. Okay, which term is dominant in this range? So let me write it again. Q equal delta T. Let me write it delta T over R insulation over plus, this is R insulation, R cylinder for insulation, plus R convection. Okay, now we said that this R convection equal to 1 over H multiplied by A. Okay, so if we keep increasing R, then this is increased. Okay, said earlier, this is the first parameter. Okay, so if we keep increasing R, then R convection decrease, and then Q will increase. And this is what happened here in this scenario. Okay, of course, if we keep increasing R, also R insulation, because it's equal ln R out, which we are keeping increase this R, okay, over Rn divided by 2 by Lk. Okay, so if we keep increasing R, this term increased, and then this resistance increase. So if this resistance increase, we expect that Q will decrease. But R insulation in this portion is not dominant. Who is dominant? R convection. Okay, R convection is dominant. This is why Q tend to increase up to this point. But here in the other range, this range, Q you can notice is decrease. So which term is dominant? R insulation. So if R insulation increase, what we expect from Q? We expect to decrease because it is in في المقام موجودة. Okay, so إذا زاد المقام, we expect that Q must decrease. So in this portion, R insulation dominant, so we expect that Q must decrease, and in this portion R convection is dominant. Okay, so the critical radius of insulation for cylindrical body is equal to K over H. So هذا القانون بدنا نحفظه. R critical for cylinder. So at this point, okay, we reach to equality. So the effect from both parameter reach to equal amount, or we reach to the maximum Q. Okay. So for example, if this is the value of most of the insolation, average value, divided by H minimum, okay, in order to calculate R critical, because here we have two effect or two parameter affecting R critical. So this is the R critical for most of the insolation. طبعا من كيس من insulation لانسوليشن هذه الفاليو بتتغير، اوكي، ما بتضلها ثابته based على السؤال اللي معنا. اوكي so if we have spherical هذه المعادله بتتغير بتصير 2k divided by h. So this is how we calculate R critical for cylinder, and this is how we calculate R critical for sphere. وين بتلزمنا هذه؟ بتلزمنا عشان أعرف أنا هل الانسوليشن اللي معاي قريب من ال R critical ولا بعيد. إذا كان أكبر ال R اللي معاي للانسوليشن اللي مستعملها السؤال أكبر، معناته أنا في أي بورشن؟ أنا في هذه البورشن، أوكي؟ بالتالي ال R insulation أكبر، وبالتالي ال Q إيش مالها؟ رايحة تقل. إذا ال R اللي معطيني إياها في السؤال أقل من ال R critical، ال R critical أكبر مثلا، أوكي؟ بالتالي أنا بهذه البورشن، بالتالي ال R convection هي الدومينانت، وبالتالي ال Q إيش مالها؟ will increase. Okay, so let's now start with example. So in this example 4, a 3 meter internal diameter, take spherical tank. Okay, here it is. Okay, so this is 3 meter. Here we have 1.5 as a radius. So as a diameter, this is a 3 meter. Okay, from here to there. Spherical tank. So this is the geometry. Made of 2 centimeter thick, and here is the thickness. So we have inner diameter or inner radius. Okay, and then we have outer radius. Okay. Okay. Thick stainless steel. So this is the material of this gray region. Okay, stainless steel, and here it is the thermal conductivity is used to store ice at temperature. So this is the infinity 0 degrees Celsius. So this is the inside temperature. The tank is located in a room whose temperature is T infinity to 22 degrees Celsius. So this is the surrounding or the environment surrounded the spherical tank. The walls of the room are also at 20 degrees Celsius. Okay, so T surrounding and T infinity the same. The outer surface of the tank is black. Okay, so this is information about, we care about this information for whom? For radiation. Okay, so the outer geometry here, the color here is black. Okay, at 5 degrees Celsius. Okay, so here temperature of surface, the surface equal 5 degrees Celsius. Okay, and heat transfer between outer surface of the tank and the surrounding is by natural convection and radiation. So here is the connection. We have convection, natural convection, and we have radiation. And once we have natural convection, that means radiation will play a very important role. The convection heat transfer coefficient of the inner and of the outer of the tank, so this is inner convection and this is outer convection respectively, determine the rate of heat transfer to the iced water in the tank. So as expected, once this temperature 0 and the surrounding temperature 22, okay, so the temperature will transfer from outside to inside. So we need to find out Q dot. Okay, so this is unknown. the amount of ice at 0 degrees Celsius that melts during a 24-hour period. If you know the heat of fusion الحرارة اللازمة للانصهار of water at atmospheric pressure is 333.7 kilojoule per kilogram. So we'll come to this part when we'll solve the first part. So what do we have here? How we'll start? So let us first move to the solving board. Here it is. Okay, and let me first draw the geometry. So here is the geometry. We have here ice inside the inner surface, and here we have stainless steel. Okay, so here is Rn. Oops. Rn, and here we have R out. Or we can name it R1 and R2, where R1 equal to 1.5 meter and R2 equal to, in the question, the thickness of this spherical geometry is 2 centimeter. Okay, so the inner radius 1.5 plus, this is 1.5 in meter, the thickness 2 centimeter. So this is 2 centimeter divided by 100 in order to convert it to meter. And then R2 will equal to 1.52 meter. Okay. Now regarding the resistance network, because sometimes in the statement of a problem they ask us to draw the resistance network. So outside we have convection and we have radiation. So I'll draw both. And once we have both, we'll have them on parallel. Okay, so this is R convection, and here we have R radiation. Okay, then we have another resistance for the stainless steel, for the shell, القشرة اللي هي هذه القشرة. Okay, so this is R for whom? For the spherical. Okay, then what do we have? We have R convection inside. Let us name it 1 and this is 2. Okay, what else on this resistance network? We have here, this is T infinity 1. Okay, and here we have T1. Here we have T surface. Okay, this is T1 here. T1. And here we have T surface. And here we have T infinity 2. Now, let us calculate the R total. So R total equal to R convection 1 plus R spherical plus we have two resistance on parallel, so the summation or the resultant of these two resistance 1 over R convection 2 plus 1 over R radiation. Okay, let us calculate now. Let us calculate them one by one. But before doing that, let me calculate the areas. Okay, so we have area 1 calculated. So this is the inner area calculated from or according to radius 1, which is equal. This is area for spherical. Okay, and this is equal 4 by multiplied by r squared. Okay, r1 squared. Okay, so if we substitute r1 1.5, we will get, let me erase this one, we'll get 28.3 meter squared. And the same will do for area 2, 4 by r2 squared, and this is equal, r2 equal to 1.52. This is equal to 29 meter squared. Okay. Okay. Now, let us start with the inner convection. Rn, or R convection n, equal to 1 over H1 area 1. This is equal 1 over H1 from the statement of this problem is 80 watt per meter squared Kelvin multiplied by area 1. Area 1 equal to 28. We just calculate area 1.3, and this is equal 0.0004. Or do you know what? Let me write it here. 0.00442 Celsius per watt. Okay. Now let us move to our spherical. And this is our conduction. Remember, this is our conduction for spherical geometry. What is the rule? The rule here, R2 minus R1 divided by 4 by R1, R2 multiplied by K. Okay, and this is equal to 1.52 minus 1.5 divided by 4 multiplied by multiplied by 15 thermal conductivity. Okay, multiplied by 1.52 multiplied by 1.5. Okay, and this is equal 0.47 Celsius per watt. Okay, so this value, if you want to say something about those values, this one and this one, the resistance is very low. That means it is conductive. Okay, there is no resistance, or the resistance is very low. Okay, now how about R convection 2? R convection 2, which is equal 1 over H2 area 2, and this is equal, from the statement of this problem, H2 equal to 10 multiplied by area 2. Area 2 in this case 29, and the answer here equal to 0.004. 0.034 degrees Celsius per watt. Now we end up with R radiation. So let us move to new page. So R radiation equal to 1 over H radiation multiplied by area 2. Okay, so we don't have H radiation. How we find H radiation? This is equal 1 over unknown multiplied by area 2, which is 29. So now we need to find out H radiation. So from the definition of H radiation, this is equal to epsilon multiplied by sigma multiplied by T of the surface, okay, squared plus T infinity 2 squared multiplied by T surface plus T infinity 2. And this is equal to 1 multiplied by, because we have here black, okay, so black surface means the emissivity equal to 1, remember, multiplied by sigma, which is constant, Stephen Boltzmann constant, which is equal to 5.67 multiplied by 10 to the minus 8, and here E surface, in the statement of the problem, it was 5 degrees Celsius. Should we substitute it Celsius? Or we must convert it to Kelvin? Yes, we must convert it to Kelvin. And this is equal to 7. So 5 plus 237 equal to 287 squared plus, now 22 plus 237, this is equal to 95 squared, okay, multiplied by 278 plus 295. Okay, so if you use your calculator, you will get 5.34 watt per meter squared, either Celsius or Kelvin. Okay, it does not matter. So let me write Kelvin. So if I want to go back to this equation and substitute it back, so this is here, okay, 5.34 multiplied by area 2, which is 29. So from here, this is equal to 0.0. Now this is equal to 0.00646. Okay, Celsius per watt. Okay, so it does not matter, as I said, Celsius or Kelvin, because it would cancel out. Okay, now I need to calculate the R total or R resultant from convection and radiation. This is equal to R 1 over R, which is equal to 1 over R convection plus 1 over R radiation. And from here, the resultant resistance from these two parallel resistors equal to 0.00225 سلسيوس. دائما نتذكر نكتب الوحدة. Okay, so R total equal to Rn or R convection 1 plus R spherical plus R resistance. Let me name it as R resistance or R resultant. So, and this is equal to 0.00274 degrees Celsius per watt. Okay. Now, in order to calculate the first requirement, which is the rate of heat transfer to the ice spherical geometry, okay, and this is equal Q dot, the amount of the rate heat transfer, equal to T infinity 2 minus T infinity 1, okay, divided by R total, and this is equal. Why we start with T infinity 2? Because heat will transfer from outside to inside. So this is 22 outside minus 0 divided by 0.00274, and this is equal to 8029 watt, okay, or joule per second. This is the first requirement. Now let us move to a new page. Now the second requirement is to find the amount of ice melted down. So let me move to the statement of the problem. So here we need to find out, let me erase everything. We need to find out the amount of ice, which is at 0 degrees Celsius, that melts. So amount of ice means we need to find out, amount means mass of the ice melted down. So this is unknown, okay, during this period, during 24-hour period. If you know that the heat of fusion of a water at atmospheric pressure, so this is the amount of heat required to convert ice to liquid. Fusion means الانصهار, okay, conversion from solid phase to liquid phase. So this one is enthalpy, okay, enthalpy of fusion. Remember thermodynamic. So let us solve this problem in the solving board. So we need the amount of ice melt. So in order to account for this, we'll use this equation, Q equal mass multiplied by H fusion. Okay, so I need mass of ice, and this is equal Q over H, but H is given. Okay, H given, which is 333.7. But the only problem now is Q. Q is not there. So in order to account for Q, but in the previous part, we could find Q dot, where Q dot is joule per second. Remember its unit, or watt, and this is equal Q over delta time. Okay, delta time. So in order to calculate Q, which is in joule, and then this one is in second, so Q equal Q dot multiplied by delta T. Okay, so now I think it's obvious that mass for the ice Okay, instead of Q I can write Q dot multiplied by delta T over H, and this is equal from previous part 8029 multiplied by delta T, which is 24 hour. Now in order to convert hour to second, we must multiply it by 3600, and this is divided by 333.7, and the answer is, remember that this one is in joule, okay, and 333.7 it is in kilojoules, so I need to multiply it by 10 to the power 3, and the answer here is 2079 kilogram. So this is mass of parts. So this is the second required. Okay. Okay, so this is the solution of this example, part A and part B. Let's see another example. Example number 5. Okay, so this example state that steam, okay, we have inside this geometry, we have steam inside, flow inside this one. So steam at this temperature, very hot steam, okay, 320 degrees Celsius, very hot, flows in a cast iron. This is the material of this pipe, cast iron. So once we are talking about pipe, then we have cylindrical geometry, and here is the thermal conductivity of the cast iron. The inner and outer diameters are 5 centimeter and D2 5.5 centimeter respectively. Okay, so the diameter is given, so we can convert this one easily to R1 and this one to R2. So divide them by 2 and divide the whole answer by 100 because we need to convert it to meter. The pipe is covered with 3 centimeter thick glass wall. So here we have insulation. Okay, so we have R1, we have R2, and this color represent the cast iron. Okay, so the gray color represent the insulation, and this insulation, its thickness is a 3 centimeter thick glass wall insulation, and the thermal conductivity, see, is very low. It is not conductive. It is its function is to do insulation. Heat is lost to the surrounding at 5 degrees Celsius. So still we have certain amount of heat lost to the surrounding. So this temperature is 320. Okay, because of high temperature, the heat will escape in this direction to the surrounding from inside to outside. Okay, even if we have insulation, it is not conductive, but its resistance is not very high to prevent all heat from escaping to outside. So the surrounding temperature is 5 degrees Celsius. Okay, so this is 5 degrees Celsius, and inside we have 320. Imagine the difference between inside and outside. How it escaped? By natural convection and radiation again, with a combined, but here this question gave us H for combined effect. Okay, so if he asks us to draw the resistance network, outside we have only one resistance, okay, because here we have combined, which is equal to 9 to 18 watt per meter squared Kelvin. Taking the heat transfer coefficient inside the pipe to be, so we have inside convection, and then we have conduction through the cast iron, and here we have conduction for the insulation, and both of them conduction, but for which geometry? For cylindrical geometry. Okay, this one convection, and this one is convection. So convection 2 and this one is convection 1. Okay, determine the rate Q dot of heat loss from the steam per unit length of the pipe. So the length of the pipe is unknown, so we'll divide everything by L. Also determine the temperature drops across the pipe shell and across the insulation. Okay, what do you mean by temperature drop across the pipe shell? So here is the pipe shell. Let me erase everything. So here is the pipe shell, and inside we have T1, outside we have T2. So we need in part 2 delta T for cast iron. Okay, again we need temperature drop for the insulation, okay, across the insulation. So we have here T2 on this side and here we have T3. So I need again temperature drop or delta T across the insulation. Okay, this one delta T for the pipe. Okay, so those are the requirements. I think it's very straightforward. Then I decide to give you this task. Okay, please focus. The task is, today is Monday and this lecture for Monday. On Wednesday we have another lecture and we have I will record the lecture for you, and we have a meeting on Zoom, live meeting. So I need from you as a bonus, okay, any one of you or all of you, I don't mind. This is a bonus for all of you if and only if you can solve this problem, okay, by doing the same as what I'm doing every day, recording videos. So اللي بدي إياه منكم تحلوا هذا السؤال وحله يكون بنفس الطريقة اللي أنا بحل لكم إياها فيه، يعني لايف. سجلوا اللي أنتوا بتحلوه ستيب باي ستيب وتبعثوا لي إياه. تحملوه على اليوتيوب، تحملوه على موقع، المهم تبعثوا لي الفيديو وأحضره قبل نهاية يوم الأربعاء. اوكي، هذا السؤال ما راح أحله، very straightforward. اوكي، بس اللي بدي إياه منكم تشتغلوا على حله. اوكي، كل واحد لحاله طبعا. إذا بتحلوه كلكم خير وبركة. سجلوه بصوتكم، تشرحوا لي كيف حليتوه ستيب باي ستيب. اوكي، طبعا حل لايف، كيف أنا بحل على السولفينج بورد، بكتب المعادلات أمامكم وبسجل بنفس الطريقة بدي منكم. اوكي، وترفعوا وتسلموه بنهاية يوم الأربعاء. اوكي، if you do so حتاخذوا بونس. هذا البونس وين حيكون؟ either على الهوموركس or على الكويزز. إن شاء الله في الأيام الجاية حطرح لكم الكويزز، حطرح لكم هوموركس. بس هذا حله هذا السؤال حيكون بونس. وإن شاء الله المرة الجاي ببلش معاكم من example number 6. اوكي، so هذا الexample ما بنفع انتوا تحلوه، أنا لازم أحل لكم. Until then, see you soon إن شاء الله.